Here we have another interesting light source. It's high pressure sodium, and it's a light source that's commonly used today for street lighting and lighting large areas, and pretty much everybody's pretty familiar with it now because of its orangish glow. Some of the newer lamps have a pinkish or a purplish color, but pretty much it has an orange color to it. And this lamp was actually developed at GE. You know, the ceramic was developed right in Niskayuna around 1958. And the first lamps, which I have a prototype of, it was actually built here in Schenectady. And they started to experiment with this lamp around 1959. They started making lamps with Lux ceramic. And what it is, the ceramic is a polycrystalline alumina oxide ceramic. It's basically, it's aluminum oxide is what it is, made into a ceramic. And the reason why they used it in high pressure sodium is because the high temperatures at which these lamps operate, quartz or glass or even ceramic, ordinary ceramic, could not withstand the heat. So they had to make a special alumina oxide ceramic to withstand the heat that the lamps generate. And basically all the lamp is a discharge lamp. It has one electrode in each end of the arc tube, and the current goes through gas. The fill gas inside is xenon gas, and there's an amalgam of mercury and sodium in the arc tube. The reason why there's mercury and sodium is for two reasons. Number one, it controls the vaporization rate of the sodium during warm-up. And number two, the mercury vapor lends its blue rays to the light to make the light less monochromatic. It's more full spectrum because it's got blue rays as well as yellow and red and orange rays. So it's technically a white light source, even though it doesn't look white. It is a type of white light source. Objects lighted by it, at least you can tell the color of them. Not that well, but you can, you know. So that was the advantage of the high pressure sodium design. Plus they're more compact and longer lasting than the old low pressure sodium lamps were, though they're not as efficient as low pressure sodium. But their advantages outweigh their disadvantages, obviously. They're an interesting lamp in that to start the lamp when it's cold, they have to pulse it with a high voltage pulse to start the arc through the lamp. So to do that, they use an external electronic circuit built into the ballast to start the lamp. It works almost like a coil on a car, how it fires a spark plug. It just hits the lamp with a high voltage spike, and that's what starts the arc. Once the arc starts, it's through xenon first. So the lamp will light up almost a sky blue color. Then it turns blue because the mercury vaporizes first. Then when the mercury generates enough heat, the sodium vaporizes last, and then the color will finally shift over to the orangish color as the sodium vaporizes into the mercury arc stream and the two colors combine, the blue and the orange combine. And then you get that purplish orange or whatever color. The lamps vary by brand, by color, so they're not all exactly the same. But the lamp has pretty good efficiency. It didn't turn out to be as high of efficiency as they originally thought. The lamp itself is very efficient, but the auxiliary equipment used with it, the ballasts, have to be very lossy because the arcs run at low voltage. So they've got to step that voltage down in the ballast. Okay, here's another high pressure sodium lamp, but this one has a little bit different design. It's actually a kind of a homeowner brand name, you know, like for the average consumer, Lights of America. And they did things a little differently. Instead of using an electronic circuit to pulse the lamp to start it, as I previously said, this lamp has, and you can see it there running along the arc tube, there's a flat strip, and then there's a little wire that runs down alongside the arc tube. And what that does is it just sets up a capacitance or a stray voltage between the arc tube and the other side of the circuit, you know, the return side of the circuit, so that the amount of voltage it takes to strike the arc through the lamp is lower, and it doesn't require a pulse to start it. In fact, the fill gas in the arc tube may be different too. It may be neon or argon instead of xenon, which strikes at a lower voltage. So you combine that with the starting strip, and the lamp doesn't require an external lamp igniter. It'll start on the voltage that the ballast puts out. This was used for the Lights of America homeowner light fixture, which makes finding replacement lamps difficult, unfortunately. But they do make larger versions of this lamp to retrofit into existing mercury vapor fixtures. Uses the same basic principle as this, and it will start and operate on a mercury vapor ballast without any external starting gear being necessary to be added to the fixture. In fact, one type, this strip is actually a heater, and there's a starter in it like a fluorescent lamp uses that blinks the current on and off to the heater, and it gains heat each time until it heats up the arc tube enough, and that helps it to strike. Plus, every time the starter opens, it creates a pulse from the ballast by the induction of the ballast, and that helps start the lamp. So some of the HPS conversion lamps to convert existing older fixtures use this principle as well. This is just another way to start an HPS lamp without having to have an igniter in the ballast. It works okay, but it has its issues too. Like sometimes the lamps don't like to start in cold weather and things like that. So it's not perfect, but it is another way to start an HPS lamp, and an interesting one at that.